All right, guys, good morning. Hope everybody's doing well on this Wednesday. We have one more section to finish in this chapter on acids and bases, and we'll be done with it today. Thursday and Friday, you guys are going to be working on the chapter review to get some good review in and good practice in before I return. And then we'll start Monday reviewing this chapter for a potential test and hopefully get that done in time so that we can have some good review for the final exam. Section C is on page 413, starts there. The title of this section is neutralization. So we're going to be talking about neutralizing or neutralization reactions, and we've kind of already talked about them in some way. A neutralization reaction is this equilibrium probably looks familiar to you. It's an acid plus a base yields or produces equilibrium, salt, and water. So we've talked about this already. The hydrogen of the acid combines with the hydroxide of the base to make the HOH. We call it H2O, the water. So it's actually a very simple process, and it's one you can figure out. I'm not going to require you to do this just because we have to go all the way back to oxidation numbers and things to that nature, and I just don't think that's necessary, but I do want to bring it to your attention. If you look on page 413, so please take your ebooks, look on page 413, right under the section entitled Salts, 16.14, you see that chemical equation, the MgOH2 magnesium hydroxide plus 2HCl hydrochloric acid. That's going to produce magnesium chloride and water. So if you look, I'll explain this how this works. It's actually very simple. The Mg combines with the Cl. Okay, so your Mg, the metal, combines with Cl, the non-metal, and that OH and the H combine from the hydroxide and from the hydrogen, and that's where you get the 2H2O on the product side, and then the Mg and the Cl combine to form the magnesium chloride, which is your salt. So if you guys remember the double replacement reactions, remember we talked about decomposition, composition, single replacement, and double replacement. This is just a double replacement reaction, and that's the process of a neutralization. But I'm not going to again require us to do this because it goes back to oxidation numbers, and it's just a little bit too much at this point in the year. But it's actually very simple to figure out. Salt means, whenever I use the term salt, it's defined there on page 413 for you. It means whatever is left of an acid plus whatever is left of a base. So when the hydrogen mixes with the hydroxide, it's whatever is left with that acid and whatever is left with the base. In the example we just talked about, it was magnesium that was left over and chlorine that was left over, and those two combined to form the magnesium chloride, the salt. So that's the technical definition of a salt. Some textbooks will define it as a metal and a nonmetal. So you have magnesium, which is a nonmetal, and then you have chlorine, which is magnesium, which is a metal, combined with chlorine, which is a nonmetal. Those combine to give you a salt. Some textbooks define it as that. But this textbook defines it as whatever is left over in equilibrium. And here's another example just to show you how this works. Okay, and again, this is not hard. Here you have hydrochloric acid plus sodium hydroxide. So this is the acid, this is the base. The reason we know this is an acid is because it begins with hydrogen bonded to a nonmetal. Here you have a metal bonded to hydroxide. Remember, this is not always the way to tell it. Not everything that has hydrogen is an acid. Not everything that has OH is a base. But this example it is. So remember what I told you. The hydrogen here is going to separate from the chlorine, and it's going to bond with the OH right here, the HOH. Okay. So what's left over? The chlorine and the sodium are left over. So they're going to combine to form sodium chloride. And then you just rewrite the HOH as water, and you're done. That's the salt right there. Sodium, a metal, and chlorine, a nonmetal. So you can see it's actually pretty simple. But you do have to worry about oxidation numbers. You do have to worry about different coefficients, balancing the equations. So there's a lot more to it than just flipping a couple things around. but it's actually not that difficult of a process. All right, let's talk about salt a little bit more. There are 3 basic types of salts. Make sure you get these down. There are acidic, basic, and neutral salts. Acidic, basic, and neutral salts. Neutral salts, we'll go in the order. Acidic salts are salts that are produced by the neutralization of a weak base and a strong acid. So make sure you get that down. I don't know if it's actually defined in the textbook anywhere, but I do want you to know what they are. So an acidic base, they are produced by neutralizing a weak base and a strong acid. It's easy to remember that. It's a weak base and a strong acid, so the strong one is going to win out and it's going to produce that type of a salt. So if it is a weak base and a strong acid, it will produce an acidic base. Knowing that, you probably can figure out what a basic is. A basic salt is when it is a strong base and a weak acid. So the strong base and the weak acid combine, you're going to have a little extra of the basic nature of it left over, so that's why it's going to be a basic salt. And then the neutral is pretty straightforward. It's a weak acid and a weak base, or a strong base and a strong acid that combine to give you that neutral component. Basically, they're evenly matched, okay, is the important thing. Okay, when the acid and bases are mixed, the stronger one determines the type of salt produced. That's what I just talked about. If the acid is stronger than the base, it's an acidic base, or acidic salt. If the base is stronger than the acid, then it's a basic salt. Okay, what do acids neutralize? What do acids neutralize? We talked about this. Think about that equilibrium. We already have written down something plus something yields something plus something. So what do acids neutralize? Acids neutralize bases. That's right. Now they produce salt and they produce water, but acids neutralize bases. Okay, let's move on to a term, titration here. But before we do, I want to bring your attention to page 414. It talks about heartburn and acid reflux. This is a pretty interesting little section here. We're not going to take time to read this facet of chemistry, but it's actually pretty interesting. A lot of people suffer from acid reflux. And really all I want you to know in this particular facet here is what it's called. This is in the 3rd column on page 414 in the little orange section right next to the picture of the stomach there. It says, today an increasing number of people are diagnosed with gastroesophageal reflux disease, commonly called GERD, or acid reflux. And you can see what happens in the picture. You have it's called the lower esophageal sphincter. Probably remember the term sphincter from biology class. A sphincter is just a muscle in the body that closes. It could close a valve, it could close a tube, it could close a lot of different things, but it's a muscle. And at the top of your stomach, you have something called the lower esophageal sphincter. Sometimes it's called the cardiac sphincter, just depending on what we're talking about, what portion of the esophagus we're talking about. But that the LES, the lower esophageal sphincter, it's what allows the stomach to close and open. And obviously it would need to open for food to go into the stomach, but it would need to close while that food is being digested. Because when it's being digested, there are those gastric juices that are being pumped into the stomach. The hydrochloric acid is pumped in there, and it starts to kill all the bacteria and start the further breaking down of food, the digestion of the food. But when that LES is open, some of that gas, the acid, spews out into the esophagus, and that's what actually causes heartburn. So if you ever have heartburn, you have a problem. More than likely, if it's a continual thing, you have a problem with that LES, and it's something that you have to take some medicine for in order to neutralize that acid. It can be very serious. It can actually go up into your vocal cords and basically deteriorate and eat away your vocal cords, and you can lose your voice. And it's pretty severe. Those are pretty severe cases, but they can be very, very severe. All right, we're going to move on to titrations. This is on page 415. What is a titration? A titration is basically it's a process in determining an unknown concentration of a solution by measuring its capacity to react with a solution of a known concentration. So if you know the molarity of one concentration, and then you can react that with the unknown concentration solution, and then you can actually figure out what the concentration is. It's a very simple process. This is done when mixing acids and bases. So if you know the molarity of your base and you're trying to figure out the molarity of the acid, you basically keep adding drops of that base to the acid in order to figure out what it's going to be equal to. It's a very simple process, but very effective and used quite a bit. There is something called a titration curve, and you'll see a picture of this on 416. So flip over there, and you see that titration curve at the bottom of the page. That shows how the pH changes when you add acids and bases to a solution. So you can see what they're doing there in the textbook with that specific graph. The vertical column there is pH, so it's testing the pH of something. And then you have the molarity of the base on the bottom on the x-axis, and you're trying to figure out the titration of 0.5 molar solution of hydrochloric acid. Now with titration, as you guys probably can figure out, but let me ask you the question, what do you think you can add to the substance? If you look on page 416, you'll see the picture of the actual titration process. They have that Erlenmeyer flask filled with a solution that they don't know necessarily what the pH is, and it's dropping it into that liquid, and you'll see that there's some purple stuff at the bottom of that Erlenmeyer flask. Anybody want to take a stab at what you think that is? And yes, it's okay to answer if you think you really know what the answer is. Well, that would be what we talked about yesterday. That's an indicator, because when you add that indicator, it's going to change as you keep adding those drops because the pH is going to change. So a titration curve is a curve that shows the change with the addition of an acid or a base, or vice versa, depending on what you're doing. So here's an example here, a titration curve. You have sodium hydroxide plus hydrochloric acid yields sodium chloride and water. Here you have the pH, as I talked about. Here's the volume of the acid, depending on what we're talking about, or it could be the volume of the base, depending on what you're titrating. So as you keep adding more acid, if you increase the acid here, and use my little mouse here, the little arrow as an example, as you follow along here, and again, as I'm going to the right, I'm increasing this 1, 2, 3, 4, 5, 6, 7 on a number line. As I'm increasing the volume of the acid, I'm dropping in more acid into that Erlenmeyer flask in essence. I'm dropping the pH. So the pH is going down on this particular one, and then it's going to reach this point of a neutral solution. And then I can continue it if I want to follow it out to figure out what the true titration is for that particular substance. That's kind of how it works. You're just adding drops to it in order to increase or decrease what you're looking for. Now, you will reach something called the equivalence point. The equivalence point is the point at which the number of hydronium ions equals the hydroxide ions. Get that down in your notes, very important. Equivalence point is equal to, it's when the hydronium ions and the hydroxide ions in that solution are equal. Okay, so you get a neutral pH, but the equivalents of the H3O positive and the OH negative are equal. So please make sure you get that. Equivalence point, the point at which there equals the equal amount of acid and bases in terms of pH, so the pH would be equal to 7. Endpoint is also a term on page 416, the point at which a titration is stopped once the indicator changes color. So you add the indicator to determine whichever indicator you use specifically to the pH that you're trying to get. But once it reaches that point, it's called the endpoint. So if the pH changed, let's say the indicator changed when you got to a pH of 5, well, that would be the endpoint. Let's say, I'm just making this up, let's say it turned purple when it got to a pH of 5, okay? The indicator changed purple. Well, that would be the endpoint. It would be 5. So that would tell you what the pH is of that particular solution. Okay, so why would you do titration? Why would you do titration? To find the pH, to mix acids and bases, to see if a buffer is needed, or to find out the concentration. Why do we use titration? Titration is used to show the pH of the change in the pH of the total solution. So I'm not quite sure what happened to my slide there. All right, titration calculations. You'll enjoy this. This is very simple. At least I think you'll find it very easy. You can actually calculate the titration mathematically. Here's a formula. It's molarity times volume. So to find the concentration of any solution, it's equal to the molarity times the volume. So you'll see another equation. This is one that's also in the textbook. The molarity of the subscript K here stands for known, okay? So it's the molarity of the known times the volume of the known equals the molarity of the unknown times the volume of the unknown. This is very simple because I will give you all the pieces except the one you need to solve for, okay? So I'll give you the molarity, I'll give you the volume. I may ask you to find the molarity or the volume of the other one, depending on whatever the question asks for. So this is a very simple application. All right, let's take a look at a sample problem here to see how this works. If a 52.4 milliliter of a 2.13 molar hydrochloric solution is titrated with a 76.9 milliliter of a sodium hydroxide solution, what is the concentration of sodium hydroxide? Now remember, don't forget, do not forget what concentration means, okay? Concentration means molarity, okay? Concentration means molarity. So here, guys, again, this is very simple. This is your known volume. This is your known molarity. This is your unknown, because it's linked with the unknown part. It's your unknown volume, and you're looking for the unknown concentration. Very simple process. First, write the formula down. Molarity of the known times the volume of the known equals molarity of the unknown times the volume of the unknown. You had the known, 2.13 molarity, 52.7 milliliters equals the molarity of the unknown times the volume of the unknown. Simple algebra here. They go ahead and what the slide does is multiply those two numbers to get 112 equals mu 76.9. You guys can do basic algebra here. Divide both sides by 76.9, and when you do, you get 1.46 molarity of, or molar solution of, sodium hydroxide. So titration mathematically is very, very easy. Okay. We won't take the time to do this one. I won't write it all out, but you can, well, I'll tell you what, I'll give you a second or two to figure this out. See if y'all can do this one for me. So take out some paper. You can do it right there in your notes, whatever's easiest. If 24.9 milliliters of a 1.34 molar hydrochloric acid is titrated with 17.8 milliliters of sodium hydroxide, what is the concentration, the molar concentration, that's what the brackets stand for, of the sodium hydroxide? All right, so I'll give you a couple seconds to figure this one out. This should not take you very long. Get your calculators out if you don't have them out already. I'll remind you quickly of the formula in case you forgot. It's the molarity of the known times the volume of the known equals the molarity of the unknown times the volume of the unknown. So write all that down. Calculate what your answer is going to be. I'll give you about 15 seconds to do this. Okay, that's 15 seconds, so let's see what we got here. You calculate all that information, and you should get 1.87 for your final answer for that particular problem. Here I went ahead and showed you the solution, so you can see what we did. 24.9 was the known volume, 1.34 moles where mole solution was this known molarity. And then we knew the unknown part. We knew the volume 17.8. You do the algebra, and you get the 1.87. Okay, so that's pretty simple, not too bad. Let's go through these slides here. This is the titration curve that you see. There's the indicator that is used. You can use something called Cresol green or phenethylene. Either one of those can work. And then this is the titration process. So this is the substance that you'd be adding to this 100 milliliters of the 0.5 moles hydrochloric acid. You're increasing. You get to this point, which hopefully you remember, when the pH is 7. It's called, if you guys can remember, I hope you can remember, it's called the equivalence point. Okay? This section right here would be the end point. Okay, that's the end point of the Cresol green, and then you have this portion here, which would be classified as the end point of the phenethylene. So there's the equivalence point right there. Okay. All right. You can also do it based on the concentration, the mole concentration. I'm trying to get through these samples here quickly so we can look at the final component to this section. I don't think you guys are going to have too much trouble on this part. All right, the final part to this section is buffers. All right, buffers are very, very important. What do? They help keep the pH fairly constant, not necessarily neutral when small amounts of acids and bases are added. Please make sure you get this definition down and make sure you get it down correctly. Buffers help keep the pH constant. Not neutral necessarily, but constant. Okay, so let's say the pH of a solution was 4. Okay, well that's an acidic solution. Okay, everybody should remember that 0 to 7 is acidic. So 4 would be acidic. If I start adding a base to that, what's going to happen to the pH? Well, the pH should increase. It should go up because I'm adding a base to it. But let's say I didn't want it to go up. Let's say I needed to add that base to it, but I didn't want the pH to go up. Well, that's where buffers come into play. And you have a lot of different buffers in your body. The most important one is found in your blood because it helps keep your blood to have the proper pH. Because if your pH in your blood is not correct, you're going to have a very big problem on your hands. So your body has buffers to help regulate the different acids and bases that are released in your body. So it's extremely important. But you got to remember, buffers keep pH constant. So if the pH is 10 and you want to keep it constant and you're adding an acid or a base to it, because if you add a base to 10, it's going to increase. If you add an acid to it, it's going to decrease. But let's say you wanted it to remain 10, you add a buffer to the system. Very important. They consist of weak acids and its conjugate base or the opposite combination. So they consist of weak acids and its conjugate base. The weak acid neutralizes a base when it's added, and the conjugate base neutralizes the acid and added acid. This kind of goes back to that conjugate pairs, okay? The weak acid neutralizes a base when it's added. So it's kind of neutralizing that base because, again, it goes back to what I just said. And again, this isn't too confusing. You just have to think. If I have a base and the base is a weak base would be considered, it doesn't matter. It could be a strong base. Whatever it is. Let's say the base, the pH is 9. If I add an acid to that, it's going to neutralize it because remember, if you add the acid to the base, it's going to go back down toward that 7. So that's kind of what it does. It keeps it regulated. So that's extremely important. That kind of concludes what we're going to be talking about this chapter. So it's pretty straightforward, pretty basic there. Last section's not too bad, just a couple terms, and I think everybody neutralization reactions and titrations, calculating it, I think you kind of comprehend all that stuff, so I don't think it'll be too bad. Well, that concludes the chapter, okay? What I want you guys to do for homework, I know it's Wednesday, but you probably have some time right now in class. For the remainder of class, what I want you to do is section review 16C. That'll help you strengthen your understanding of what was covered today. So again, what I want you guys to complete for me is section review 16C. And I hope you guys have a great day. It's Wednesday, just 2 more days this week, and I'll see you on Monday.